A second property that we like to see in good estimators is consistency. So as the sample size increases, the sampling distribution of the estimator needs to tighten more and more around the true value of the population parameter. So as our sample size gets bigger, we're more and more confident that our estimate is close to the true population parameter. So going back to our original example with household income in the US, we know that the true population parameter is $44,000. Our sample size that we used before was 100, and the sampling distribution we know is normal, and it will look something like this, with most of the mass of this distribution around the true mean. But there'll be some estimates that are lower than the 44,000, and some estimates that will come back higher than the 44,000. But mostly it's centered around the true population parameter of 44,000. Now, if I were to increase my sample size to 200, the mean of this sampling distribution will still be centered around 44,000. However, more of the mass will be closer to 44,000 than when my sample size was 100. So I still have some estimates that are producing numbers that are smaller than 44,000 or larger than 44,000. But more of the mass of my distribution is now closer to the true population parameter of 44,000. And then kind of continuing on here, if I increase the sample size even more to 1,000, then I get even more of my mass around my true population parameter. And the tails are even smaller in this case. And this should make intuitive sense as well. As my sample size goes up, I'm more and more confident that my estimate is closer to the true population parameter. And that's going to be the case with any consistent estimator. Note that the four estimators we talked about previously as being unbiased, that is sample mean, sample proportion, difference in sample means, difference in sample proportions, those are also consistent estimators of their respective population parameters.